So since the last video, we have an antenna in the air, and I've been able to build up the little transmitter fully, and we'll go through that step by step in this video. Now, as you can remember, I substituted the 6CL6 tube for the original one in the article. I thought that perhaps this tube would put out a little more power at lower voltage. And I can tell you, it did happen. This thing puts out 1 watt with essentially half the voltage that the little peanut tube was using. So I can say it gets pretty hot. So I can't imagine what the little peanut tube was doing with 700 volts on it. But with close to 400 volts on this guy, it gets pretty warm, but it's well within the dissipation of the tube. Some foreshadowing, however, a couple of issues. First of all, I don't think the 6CL6 suppressor grid modulates very well. That is, it's not responding well to variations in the suppressor grid to cut the tube off and affect modulation. Some tubes are good, some tubes are not so good at suppressor grid modulation. For instance, beam power tubes are notoriously bad. Old-fashioned power pentodes are usually the best ones that have a separate suppressor grid, like the 837, for instance. So I may well have to substitute a different tube for the 6CL6 by the next video. But let's see how I got this far. First of all, Mike, it looks like you've added 15 parts to the simple one-tube schematic from the original book. Well, touche, that's for sure. Remember, we said this is a one-tube project, but in order to make it safe, cut down on the possibility of a bad signal, and adding the relay feature, which gives us that changeover with the microphone. It takes a few parts. Fortunately, we haven't had to change the transformer, and I think we have plenty of juice to be able to do this with the simple circuit. But yes, there are more parts. It's only fair that we start with the original schematic and with the original tube, the 6BH6, which is a small RF sharp cutoff pentode. And as you can see, it has a separate suppressor grid, pin 7. Now in the original schematic, they're developing the high voltage with the voltage doubler. They're developing the negative bias for the suppressor grid modulation with this resistor, the 4.7K. And they're delivering some 6 volts DC to the carbon microphone. Presumably, as you talk into the carbon mic, the voltage is increased through the transformer and it modulates the suppressor grid, cutting off the tube and causing upward and downward modulation. Now you have to set this bias point critically so that it's about at the half power point. So if this were a 1 watt output transmitter, the first thing you would do is make sure that you have the bias set up so that it's operating probably around 500 milliwatts output, and that gives you some place to modulate up and down. So let's go to the modified schematic. This is what I am trying to build, and we have all kinds of interesting features here. With the addition of the relay, it allows us to do antenna changeover and receiver muting with this shorting switch. A mute switch for the receiver itself if you want to use it. And we have a final relay, which is the actual application of the high voltage to the screen and plate of the 6CL6, which causes it to transmit. We'll be building up the tri-tet oscillator, which is tripling this frequency in the tank. So I've added some on-off features here. There's a off standby transmit switch. It's a double pull, double throw, on, off, on toggle. I originally had 3 sections in this, but you really only need 2. So I think we're ready to start working with the circuit. The first thing we're going to do is build up the high voltage power supply off the transformer and see if we can get some voltage up here on the plate. We're looking for something around 400 volts. Okay, this morning I've got the old military radio net going in the background, but this is the moment of truth on the power supply section of our little transmitter. You might remember the power supply section involved an interesting voltage doubler system which produced a negative bias voltage, and there are a few positive voltages that are produced low voltages off the 6.3 volt filament line. So it's a fairly complex power supply for a small box. So this is the bring up, and typically I like to use a variac, and the variac has a small fuse in it, so it's going to pop if something crazy happens. So the first thing I'm going to get on is the high voltage, because that's the one I'm most concerned about, because that is a voltage doubler. So I'm going to gently bring up the voltage. Okay, I'm at about the 10% point of the variac, and we already have 41 volts. That's a very good sign. Maybe up to 100 volts or so. Okay, so we're up around the 20 to 25% point on the variac, and we've already got 100 volts, so it's certainly doubling. Let's look at some of the other voltages. One of them is the negative bias voltage. That should be negative. Let's see if we can get on that. Yeah, negative 6.5. So we have a combination of voltages. Nothing is burning up. Everything seems pretty happy. Let's try to bring the high voltage up full. And I'm very carefully going to connect to that without getting a shock. Okay, we're still at 100 volts. Let's keep bringing that up. About the 70% point, we get about 257. We're over 300 volts. And we top out at 365 volts on the high voltage. I'm carefully going to take it down again. I have a bleeder resistor I've added to the circuit. Let's see if that works. Okay, it's just a soft bleed, but enough to save you. It brings it down within 30 seconds. And of course the all-important on-off switch test. Okay, here's the standby switch. And here is the transmit switch. They both light up nicely, so I'm happy with that. So again, we want to look at the safety bleed. Okay, here we are, full output power, full voltage. Get the variac up full. Okay, about 370 volts. Off in the middle. Okay, count this down. Okay, that's about 20 seconds to safety. Well, I found a late mistake. Looks like I hogged too much metal. If you look at the schematic, we only really need 2 connectors. We need one connector for the receiver and one connector for the antenna, because the third connection represents the transmitter itself. So I didn't need 3 connectors, I only need 2. One for the receiver, which is the BNC, and one for the antenna, which is the SO239. So this one comes off. So now I have this hole to fill. But fortunately, I started to run out of room inside because I wanted to put my microphone transformer someplace. But it's actually best not to stick this inside where it wastes space, but to actually mount it on the outside. So I'm going to use that hole to mount the microphone transformer. So it's one of those happy accidents that we have in the WU2D construction process. Again, because I'm fairly lazy, I'm using the grid dip, gate dip oscillator to come up with some type of a tank coil for the 10-meter transmitter. I found a nice little piece of very tiny mini ductor. You know, it looks like it has enough turns to resonate in this band. We can get a nice link off this, maybe 2 or 3 turns, with a trimmer for loading control. I've got a fixed 22 picofarad cap on here, and I tried a 12 puff at first, and it was resonating somewhere up around 39 or 40 megahertz. So with this 22, let's see where we can get this to resonate. I hope you can see the grid dip oscillator. So let's move that till we get a dip. There we go. That's a good one. And let's read it. It looks to be between 25 and 30 megahertz. So that's a good indication that a 35 puff trimmer, for instance, would be a good way to resonate this, because it looks like it needs somewhere around probably 18 or 20 puff to resonate it at 29 megahertz. Maybe even lower once we get the loading on it and the tube's capacitance. But we're in the ballpark with that 22 puff, and we'll be using a 35 puff trimmer for adjusting the tank. Well, the little box is built, and let me tell you, finishing it off was tricky. Before I, again bring up the power supply on the Variac and attempt to, get some oscillations out of it, we do need to trace the wiring. And as you can see, the technique is basically you use a marker of some kind, and you trace each wire, and you use your meter, and you buzz out the wires. Okay, this is called buzzing, and you have it in the beep mode, and you just make sure that you've got basic connectivity. I'll tell you where a lot of errors are made. It doesn't really matter the size of the box. You could have a giant box with all kinds of room. It's going to be the contacts of the relay and the tube pinout. I can't tell you how many errors, copy errors, starting to count the pins backwards because the tube socket's upside down. All kinds of things happen with tube sockets, and most of your errors are right on the tube socket. So if you're having problems, double check that. So when we finally do apply power with the Variac, the next thing we'll be looking for is voltages on the pins. We need the filament voltage to show up. You don't need to be at full power for this. You can, operate maybe at a quarter of the voltage and be able to tell things are hooked up. Once you've done those basic steps of the buzz out and the basic voltage checks, next you want to plug in the relay, or you could plug in the tube first and just see if it lights up. You're not going to have high voltage because high voltage goes through the relay, but you could put the tube in and see if it lights up. That's a test. Once you put the relay in, we can put it in the constant on position. It will not need the microphone to have the relay actuated. It's going to be actuated basically by this contact on the switch. So as soon as you bring up power high enough, you'll hear the relay click. Now there will be high voltage. So you can do that with the tube out and then check the pins again. Now you will see your screen voltage, you'll see your plate voltage. So along the way, I did do some safety considerations. One thing that was bothering me was the main tuning on the output network. I chose to do a air coil. With an air coil, you need to use a variable capacitor to resonate it. And we could use a trimmer underneath the chassis, but I wanted something that was available right on top here. Something that's easy to tune with a screwdriver. Now, if I had hooked it up, as shown in the original schematic, with the capacitor simply across the coil, both sides of the cap would be at high voltage. So this point right here would be at 400 volts, and this is ground, it's very easy to get your finger across that and get a shock, or if you put a screwdriver on it, get a shock. So what I did was I hooked it up in the way that this rotor portion is ground. Okay, this is ground, and the stator portion is the high voltage portion connected to the plate. That means that both the DC and the AC RF current are on the capacitor. But fortunately, this is an air capacitor and it can take the voltage with no problem. A small film trimmer, like an inexpensive 35 puff film trimmer, you'd probably have to do it with the trimmer across the coil, and you'd have to be under the chassis or make a hole in the chassis and put it through a grommet so you don't accidentally short something out. But that's a luxury right there, having a safety feature on the top panel to tune the final output tank. Similarly, there's an output loading control, and this loading control does not have high voltage on it, but it's got some RF current on it. I wanted to be able to adjust that from the outside as well, so I have mounted that here on the side. So now we can adjust the loading from the outside world. These are little luxuries that I put in that they could have just as well been a pair of trimmer capacitors on the bottom of the chassis, but I've got them so they can be adjusted on the outside just for convenience. Similarly, here's the bias adjust. The bias set adjust is really our modulation control when you think of it, because first we're going to set that to 0 volts, which will mean full output power. Full output power for this could be 1 watt, it could be 2 watts, it might even be 3 watts. We don't know with the 6CL6 how much power we're going to get out. But once we start to put in some negative voltage on the suppressor grid, bringing negative voltage up with this pot, we're going to be setting that until the resting output power is down to, say, 1 watt. So as we talk, it will go from 1 watt as high as 2 or 3 watts, and so on, and down to, close to 0. That's what we call AM modulation. We are using all 4 sections of the 4-pole dual throw switch, which is the relay. 2 of them are used for the antenna switching and muting. This is the antenna switch part of the relay, K1A. This is the muting part, which shorts the receiver during transmit. Then we have the mute contacts, which is a simple closure when you're in transmit. That's known as a dry contact. What's a dry contact? It's an old telephone term. It simply means there's no voltage or current from a battery or a power supply on this contact. A couple more things of note. I found a 9.462 crystal. This crystal is going to get you very close to 29 megahertz, and it was just $5 or $6 on the internet. So there is a small HC49 crystal that I was able to get my hands on. Also notice I have the United Transformer Company microphone transformer glued in place effectively, but it still needs to be grounded, so the outside of the shell is grounded to the chassis with this little link. Okay, the relay is installed. I did the buzz out. Let's bring the Variac up. I'm in the constant transmit mode without the mic. At some point we should hear the click of the relay. There it goes. Okay, so on pin 9, nothing. On pin 8, we have 361 volts. That's the screen. Unloaded, it's going to be the same as the plate. Then we have the grid, the suppressor grid, which should be at 0 right now, but if I adjust, it should come up slightly negative, and it does. Okay, so that simply proves that the bias is set right at 0. Then we should have the plate, yes, 360 volts on pin 6 of the 6CL6, and then the filament, which is AC, 4 and 5, so it's 9, 8, 7, 6, 5, 4. It's these two, right? 7.16 volts unloaded. Okay. So the other thing we need to check is, in the other mode, does the microphone actually key the relay? If we can get it plugged in. Okay, that's what we wanted to see. Next, we will take the voltage down, let it bleed off, and we'll plug the tube in, and we will start to put crystals in and see if we can get this thing to oscillate. So the good news is, even at half voltage, the transmitter is putting out close to a watt, and it seems to be fairly agnostic to the tube I use. The crystals seem to work fine in the tri-tet oscillator. The tuning seems good, the coupling seems good. I'm using this old SWR bridge to do the fine tuning because this is not a QRP watt meter, and it's probably not very accurate either. But at least I needed something to tell, that I'm tuning. For instance, I can get on the tuning dial here, and I can tune it. There's also a loading control on the side that I could adjust to get more output. This is the tri-tet adjust. Let me show you how this works. It's not bad. It really isn't. It's fairly easy to adjust. It's operating up around 13 or 14 megahertz, where we assumed it would work. Nothing squirrely or crazy. The oscillator came right up. So pretty good news as far as the RF goes. But the little transformer that I nailed onto the side of this, you guys remember this transformer? The ratio was nowhere near enough to produce good modulation. I figure I was getting about 10% modulation with the microphone. So you really do need a high ratio transformer. If you work out the numbers on this transformer, it's going from 50 ohms up to 15K. Well, that's a lot less than going from 4 ohms to 10K, or 4 ohms to 20K or 30K. You really need a ratio of around 100 in voltage terms to make the mic work. Or you need to have a more output carbon type than the Shure microphone. The Shure microphone is not made for raw output like a telephone carbon element is. So on my original transmitter that I made with the suppressor modulation, I used a telephone element with that transformer and had plenty of modulation. But the Shure mic is not cutting it with that little transformer. So the other thing we have that's against us is the bias. You're supposed to set the bias so that your peak power, let's say you just max this out, is approximately half of what you're putting out. So if we were putting out, say, a watt, you'd want to put out maybe something like a half a watt resting power. And with the potentiometer that I have here, it's bringing it down, but not very much. So I can't get very much modulation. So that means that that pot needs to be a bigger pot. So I tried putting a 5K pot in there. Right now I have a 2K pot in there. And the 5K, the original 10K had too much voltage. It took it right down to 0 almost. And it burned up. That's the other thing you have to be careful of. There's a lot of juice going through the potentiometer. Those new type pots with the carbon film, they simply don't hold up in this circuit. You want an old-fashioned wire-wound resistor type pot, like a 5K. A good 2-watt 5K pot, not one of these new audio styles with the carbon film. So there's some mods that we need to do to get the modulation. And I've ordered a small transformer that's got a better ratio. Hope I can make that work with the circuit. So we got RF, but we're having modulation issues already. So what does it sound like? I've got the receiver in CW mode. So if we look up on the receiver, you can see it's got a nice CW note. Let's put it in AM, see what it sounds like. up the bandwidth. When I have the volume on full, I hear some hum. Might have to address that once we get modulation. But at half volume, you don't hear anything. So we've got to get some modulation in this thing, and that's what the next video is going to be all about.